In this video, we take a look at partial derivatives, where we're going to find derivatives of functions with several variables. So unlike like y is a function of x, just one variable, we can't just take a regular derivative if the function is defined as a function of x and y. We can't just take the derivative really with respect to x. It's got kind of a different name and a different sort of setup. I want to give you the definition here. Of course, just like in Calc 1, this is a limit definition, and that's why I talked a little bit about limits in the last video, but I just want to show you the definition here. So what we have, I'll go through it quickly. If z is a function of x and y, then the first partial derivative with respect to x and y are the following. We denote this f with a subscript x at the point xy, right? And this is just going to be in general for now, and then we'll put it at a specific point later, say some point a, b, or something like that. But this is known as a partial derivative, right? Partial. So it's not kind of like a complete derivative, if that makes some sense. It's a partial derivative. I'm not looking at the derivative of the entire function. I'm looking at it with respect to one of the two variables in this case. It's a limit as the change in x goes to 0 of the quotient f of x plus delta x comma y. So in the x coordinate, I'm changing x by a little bit, subtracting what happens when I don't change x, right, f of x, y, and dividing by that small change in x, okay? That's the partial derivative of f with respect to x, and we denote it with that little subscript. I write the same thing for y here, but instead of changing the x direction, I'm changing the y direction, right? So the y coordinate of my function there has a small change. I subtract what I get when I don't change, right? So that difference, I still have a kind of this difference quotient, and I divide by the change in y, right? So these derivatives here are partial derivatives. There are first partials. That implies that we're going to be able to take second partials. We'll get to that. Basically like a second derivative. And this is, of course, as long as the limit exists, provided that these limits exist. Okay, same with the regular function, right? If the limit doesn't exist, if that derivative there does not exist, then the limit doesn't exist, and vice versa. Okay, so I want to look kind of at some examples here, but first, when we take these partials, when we do this in practice, we're not gonna look at the limit definition every time, right? But what we do for these partial derivatives here, we treat the opposite variable as a constant, okay? So for example, if I'm taking a partial derivatives of this function here, 3x minus, sorry, got ahead of myself, 3x minus x squared y squared plus 2x cubed y. If I'm taking partial derivative with respect to x, then what I'm going to do is to treat y as a constant. Okay, so I've underlined the three terms here. Each of those terms, I have to look and see if I find x's. Okay, if I do, those are my variables because I'm taking a partial derivative with respect to x. Any y's I see, they're thought of as a constant. It's just a number. So the first term there, that 3x, when I take a derivative of that with respect to x, derivative of 3x with respect to x is just 3, derivative of x is 1, right? You can just write 3 there. Excuse me. That's exactly how we're used to taking a derivative of 3x. Now, when I take a derivative of the second term, that minus x squared y squared is a constant. So I'm taking a derivative of x squared. You can think about that y squared as being a number, 4 out front, right? So really I'm kind of thinking about the derivative of a constant times x squared. Well, the negative sign is going to remain. The derivative of x squared should be a 2x, and the y squared again is a constant. That just stays there. right? So it's a constant times x squared. If it was just a constant by itself, the derivative of it would be 0. But since that constant y squared is pinned next to an x squared, when I take a derivative with respect to x, the constant stays out in front. And I see the derivative of x squared is 2x. Okay, the third term, when I add that, I see an x cubed. The 2y is a constant out front. Derivative of x cubed is going to be 3x squared. The 2 out front stays. Derivative of x cubed is a 3x squared times the constant y. So all I'm going to do now is just kind of recollect this a little nicer. I see 3 minus 2xy squared plus 2 times 3 is a 6, x squared y. There's my first partial with respect to x. Y is held constant. Okay, so it's a little bit different than what we're used to, and it takes a few examples and some practice to get used to treating that other variable as a constant. So I'll do a couple in this video today. Let's do the partial with respect to y. Here, x is kept a constant. Okay, oops. So when I look back up to my original function, I see the first term is a 3x there. With respect to y, 3x is a constant. So the derivative of that constant is 0. That's it. There's no y's in that first term. The next term, I'm subtracting the derivative of x squared y squared with respect to y. X is a constant, so x squared is treated like a constant. I leave that there, take the derivative of y squared is 2y, and the x squared stays there. It's a constant, right? So think about that x squared being something like a 3. I bring the 2 from the y squared down. 2 times 3 would give me a 6. I don't know what that x is, so I'm leaving it as just x squared, but it's a constant. The third term, 2x cubed is all a constant with respect to y. So when I take the derivative of 2x cubed y, derivative of y is just 1 with respect to y. The 2x cubed stays there. Okay, simplify just a bit. So what I have is minus 2x squared y plus 2x cubed. Okay, so there's my partial with respect to x and with respect to y. Now, just like we did with first derivatives, right? We have some notation to work through here. With first derivatives, we were able to use primes when we were just taking a derivative of a regular function of x with respect to x, okay? We're not going to be able to use prime notation here because that will be ambiguous in a multivariable case. So the notation we have is the following. Say z is a function of x and y. We denote f subscript x and f subscript y as the following. We use this kind of slanty, cursive looking d, right? It's still kind of a d. That denotes our partial derivative. So I read that symbol there. I read that quotient, partial with respect to x, partial x. So I'm taking the partial with respect to x of f of xy. That's the same as f subscript x of xy. Also, we use the notation z subscript x. You'll see that relatively frequently. Just another, so if z is my shorthand for writing out f of xy, then the partial with respect to x is z subscript x. You'll also see partial z partial x. And really then the same with y. So I see these subscripts is really probably what we use most of the time, but you will also see the partial notation, that kind of curvy d there is that what I read as partial. So that's partial of z with respect to WRT x and partial of z with respect to y. Okay, So there's some of the notation that you'll see, and I don't want to say that that's all of the notation for partial derivatives, that you'll come across if you keep going in math, but that's most of it. I'll just do another quick example with some of this notation. Say I have a function f of xy is sine of x squared y. If I take partial f partial x, that's the partial derivative of f with respect to x. So I'm taking derivative of sine of x squared y with respect to x. Sine is kind of the outside function here. So when I take a derivative, I take f subscript x. That's going to give me a cosine, right? Derivative of sine is cosine, no matter what variable I'm taking it with respect to. Inside stays the same. Chain rule. The inside function here is x squared y, and I need a derivative of that with respect to x. Okay, so the chain rule still exists here. Derivative of x squared times y. Y is a constant. Derivative of x squared with respect to x is 2x, and y is a constant. Okay, I also want the partial with respect to y. Excuse me. So in this case, I take f subscript y, derivative of sine, got ahead of myself. Derivative of sine is cosine with respect to x or y. Inside stays the same. Then the derivative of the inside with respect to y. This time x is a constant. Derivative of y with respect to y is 1. So all I should see is an x squared times a 1, or just x squared. Okay, so for that first example, this x squared y, when I took a derivative with respect to x, I got 2x, and the y just kind of came along for the ride. In the next, when I take a derivative partial with respect to y, the x squared comes down for the ride, and really there's no y there. When I take a derivative of y with respect to y, I get a 1. Okay. So now what I want to look at is how I evaluate these things, right? These guys are also functions, and I should be able to evaluate them. I should be able to look at maybe something like a slope, right? A derivative at a point. We use a similar evaluation notation as we have in the past, right? So if I take a partial z with respect to x, I use this vertical bar to denote an evaluation. So if I'm evaluating in that notation there with the partial z partial x, I use a vertical bar and evaluates at, say, the point AB. That's the same as taking a partial with respect to x with the subscript notation evaluating at AB. Okay, so it's really just about the same notation. But if I don't have just an xy in there, it's some general point, then I'm treating AB, I'm treating that as some specific point. Okay, so let's look at an example here. Given this function, f of xy is x times e to the x squared y. I got that x squared y again, that's just kind of happenstance. I want to find the partial with respect to x and y evaluated at the point where x is 1 and y is the natural log of 2. Okay, so first I need my partial derivatives. Right? I'm going to take my partial with respect to x first. And when I look back at my function here, I see an x there, and I also see an x in my exponent of that exponential, right? I need product rule here. When I take a derivative with respect to x, when x is my variable and y is my constant, each of those, I got two functions of x multiplied by one another. I need product rule. So that goes first, x times the derivative of the second, derivative of e to the x squared y with respect to x. Well, derivative of that exponential is the exponential. Chain rule times the derivative of the power with respect to x. Derivative with respect to x, or partial with respect to x, there should be a 2xy. Again, because y is constant. Plus the second function with respect to x, that exponential, times the derivative of the first function with respect to x is a 1. So then when I go to evaluate, first I'm going to try to factor here. I see an exponential in both of these terms. I'm going to factor that out. I see my partial with respect to x. When I factor out that exponential, I have 2x squared y left over plus a 1. Okay? So now I'm going to evaluate this. Now I'm just going to plug in the point when x is 1 and y is the natural log of 2. So f subscript x evaluated at that point. For x, I'm going to plug in 1, and for y, I plug in natural log of 2. So I see this. And now to crunch the numbers, right? So what I have really here, the exponential, is e to just the natural log of 2 times, in parentheses here, 2 times 1 is 2 times natural log of 2. I get that guy there. And thankfully, I know e to the natural log of 2 is just a 2. And then in parentheses there, 2 natural log of 2 plus 1. So there's the derivative evaluated at some specific point, and it's that value. I could find an approximation if I wanted to, but there it is in exact form. Now to look at the partial derivative with respect to y, and then plug in that 0.1 natural log of 2. Here, when I go to take a derivative, those two terms, both of them don't have a y, right? The only one with a y involved, the only one with the variable I'm talking about, is the exponential. So really, when I take a derivative here, I do not need product rule anymore. So when I take my partial derivative, f subscript y, the x stays out front. The derivative of this exponential is the exponential. Chain rule times the derivative of the exponent with respect to y just gives me an x squared. Right? I do not need product rule here, okay, because there's not a y both kind of out front and a y in the exponent. I just have one y. The x's are constant everywhere else. Let's just simplify a little bit. X times e to the x squared y times x squared is x cubed e to the x squared y. So now when I plug in 1 natural log of 2 for in my partial derivative here, x is 1, and that happens twice, and y is natural log of 2. So the 1 cubed out front is just a 1, and in the exponent, I have just a natural log of 2. All of that is 2. That's it. Just 2. So what we have here is something very similar to what we had in the one or two-dimensional case when I took a derivative of y with respect to x. I had a slope at a specific point. Okay, so this is a little bit different. Here, f of xy really gives me a surface. So the derivative at a point, some xy location, is the slope of the surface in a specific direction. So kind of informally here, without giving the complete definition, partial f partial x and partial f partial y denote the slope, the rate of change of the surface here. Instead of just the curve, the surface in the x direction and the y direction. Okay? So really, what's going on is slightly different. So the slope of fxy, the function that I used in this last example, in the y direction is just 2. At the point, 1 natural log of 2 is just 2. So at that point, on the xy plane, on my surface, that's defined by f of xy is x e to the x squared y. The slope in the y direction is just 2. Okay? So I could talk about the slope in the x direction, not really the z direction, right? That doesn't make that much sense in this case. But my surface here, I can look at slopes in specific directions. Okay, we can still kind of try to find critical points or mins and maxes of these multivariable functions. That's something you'll look more into in Calc 3, but it has to do when the slopes are 0 simultaneously, right? So when the slope of in the x direction and y direction are both 0 at the same time, I should be at either kind of a high or low point, or maybe what we'll call kind of a saddle point. maybe we're kind of misled and there's not really a max or min. It's just kind of changing some inflection a little bit. But there's some examples of partial derivatives with respect to x and y. In the next video here, I'll go and look at kind of what we call second order or higher order partial derivatives. Thanks for watching.